my pleasure to introduce our speaker for tonight. She is both a friend and also is at the university that is my alumnus, go Pokes, Dr. Camila Knapp. Dr. Knapp is professor of geophysics and serves as the V. Brown Monette Chair of Petroleum Geology. She's also head of the Boone Pickens School of Geology at OSU. She received a PhD in geophysics from Cornell and a BS in geophysical engineering from the University of Bucharest in Romania. She's a Fulbright fellow at Cornell, and early on she worked with the Romanian State Oil Company and the Romanian National Institute for Earth Physics, which I think is just awesome. She was 18 years at the University of South Carolina, where she was a professor and the director of the Earth Sciences and the Resource Institute. She came to Oklahoma State about 3.5 years ago, and the program is just doing awesome under her. So this evening, she's going to be speaking to us about seismic inversion for carbon storage in the South Atlantic offshore region, and then showing its application to the Anadarko Basin in Oklahoma. So Dr. Knapp, it's all yours. I'm going to stop sharing my screen.
Authors, many students, some of them at the University of South Carolina, they finished there. Some of them came here with us at OSU, but most of the let's say the bulk of the work is done by Khaled Al-Mutairi, who is now with the King Abdulaziz City for Science and Technology. He just visited actually like 3 weeks ago. He came to see us. He came to the US and he took a trip here at OSU, a great friend. And then also I will show some of the recent work done by Peyton Pruitt, who just defended her master's thesis, replicating the workflow that I'm going to present for the Anadarko Basin. Acknowledgments, many institutions who contributed to these projects, but in particular, I would like to acknowledge the Department of Energy for the funding and the Southern States Energy Board for their leadership on the project. I hope I don't forget, but when I'm going to talk about the Anadarko Basin, we did use data from EOG that were acquired actually by Cytel. That's the disclaimer from DOE. And I will start by highlighting the 4 large DOE projects that I've been involved with starting in 2009. We started onshore to characterize the South Georgia Rift Basin in South Carolina. And that was a $10 million project involving 2D, 3D seismic and drilling a borehole. Then the Southeast Offshore Storage Resource Assessment that I'm going to present parts of it, today. We just finalized that project, and now all of this data is in the public domain. And then 2 projects that are ongoing here at OSU. We brought this with us from South Carolina and joined the project that Jack Passion had here. So we have now a larger presence in CCUS research here at OSU. I thought I would just, put some highlights in here. I'm sure you all hear about with carbon, and climate and everything, but ExxonMobil, since Patty was with ExxonMobil, ExxonMobil Low Carbon Solutions business, they are committed to invest $3 billion over the next 4 years on lower emission energy solutions. Occidental, they are really big on reaching net zero emissions by the mid-century. Tesla, of course, Tesla, is committed to that, although, those batteries, they kind of need to do something about them. Saudi Aramco, that's from their homepage. They believe that, CCUS will play a key role in global efforts to reduce emissions, while ensuring the world can continue to thrive. And I think, that's the the take-home message, because the world needs to thrive. And, we all need to find solutions for that. And when I say all, we come from the academic field, but we definitely work in the industry. That's where where the solutions really are and will be developed. I like to show this slide, to our students and in some talks, but global energy demand in 2020 fell by 4%, the largest decline since World War II and the largest ever absolute decline. But according to the U.S. Energy Information Administration 2020, that was a report that they came up with, while COVID restrictions are lifted, hopefully, they are now definitely, in Oklahoma and other states, and economies recover, energy demand is expected to rebound by 4.6%. So basically, larger than the pre-COVID levels. But bottom line is that even as of 2020, as shown in here, more than 80% of the global energy consumption comes from fossil fuels. More than 25% of that comes from coal, about 27%. And CCUS works well with point sources of carbon dioxide emissions. But shown here on the right side, you also see transportation, agriculture, mostly coming from cows, agricultural soils, rice production. So there is a mix in the world energy consumption and the total U.S. greenhouse gas emissions, just in general. I thought I would show this. This is from 2019, where the energy consumption comes in Oklahoma from. And Oklahoma is an energy state, just like Texas, and you can see here fossil fuels, natural gas, predominant, coal, gasoline, basically oil products, and kind of very little hydro, biomass, and wind. So basically. In 2019, Oklahoma ranked second after Texas in total electricity net generation from wind, which is great, but still, hard to catch up with the other fossil fuel resources. And here is Texas, very similar in terms of ratios, but here we are looking at a much larger scale because, of course, it's a much larger state. Last week I gave a talk at the University of Kentucky, for their colloquium, and there you see coal, kind of going all the way, and then, natural gas and other petroleum products. But that's, basically where energy comes from. And I'm sure you all know about that, when we talk to our students, we need to impress on that, we need to find solutions because we are not going to turn that valve, anytime soon. We just need to find best solutions. The U.S. Energy Information Administration published this report earlier last year, predicting that energy-related carbon dioxide emissions will increase in the industrial sector as a result of increased natural gas consumption, but will remain relatively flat in other sectors and fuels through 2050. The Paris Agreement, you all heard about it. It's a legally binding international treaty on climate change. We were in and then we are out, and now we are back in as of January of 2021. It was adopted in December of 2015 by 196 parties and entered into force in November 2016. The idea here is that we need to come back to 2 degrees Celsius. Actually, right now it's more like 1.5 degrees Celsius scenario, basically going back to the pre-industrial era. So here on the left side shows the world large-scale CCUS facilities operating and in development worldwide between 2010 and 2020. And in 2020, there were 21 operating facilities, 3 under construction, 17 in advanced development, and 24 in early development. Here on the right side are the DOE-funded carbon storage assurance facility enterprise or carbon safe, so we call them carbon safe initiative projects. They are focused on development of geologic storage site for the storage of 50 plus million metric tons of carbon dioxide from industrial sources. They are divided in feasibility and pre-feasibility projects. And here I show the 6 with the numbers that correspond here to the map feasibility projects that are now in the phases 3 and 4, which are the more mature phases for basically commercial deployment. You may have seen this. Actually, I was talking with Joseph today. If this really is the source, this is the source I've always used, but it would be a DOE sketch here. But what are the geologic storage options? Basically, depleted oil and gas reservoirs, reservoirs that have sub-economic productions, like the EORs. Deep saline aquifers, and basically DOE thinks that that's where the future is, for meeting the net zero carbon solutions. Okay, so coal bed methane, other options here like igneous rocks or unconventional reservoirs, and offshore reservoirs like I'm going to show today. But most of these options shown here reside onshore and offshore. Okay, sorry, I'm trying. Okay. Okay, so I'm going to start talking about our project, Southeast Offshore Storage Resource Assessment, or SOSRA. This project is focused on assessing the mid to South Atlantic and Eastern Gulf of Mexico offshore resources for CO2 storage. And based on this study, on a study by Smith et al. 2008, 2 potential CO2 reservoirs were identified in geologic strata below the Atlantic continental shelf in the upper and lower Cretaceous layers. And Hills and Passion in 2010 suggested that the mid to South Atlantic margin could store, these amounts of CO2. And when we were in South Carolina, my husband, Jim and I, so we were in charge with the Southeastern Atlantic, and then Jack Passion, who studied at Alabama, and then he moved here at Oklahoma State. He was in charge with the Eastern Gulf of Mexico, and then we converged here at OSU. So we combined, we've been studying all of this area for carbon storage resource assessment. Now, just briefly here about the geology of the Eastern North American margin. So the geology of the offshore area of the southeastern United States is complex, and it was well summarized by Poe in 1978. Following the latest collisional event of Laurentia and Gondwana at the end of the Paleozoic, continental rifting began in the early Mesozoic as part of the breakup of Pangaea. And locally, this involved tectonic subsidence in restricted extensional basins, followed by thermal subsidence along the Eastern North American margin that probably ended before the Cretaceous, but we believe that before the coastal plain, sediments were deposited and are pervasive on these margins. Stratigraphic sequences on this passive margin are characterized by extensive lateral continuity and relatively minor structural disruption, which is good for CO2 storage. And the oldest post-rip sediments above what's called the post-rip unconformity are of Jurassic age and are the product of rapid plastic sedimentation from erosion, followed by a period of evaporite deposition and subsequent initiation of widespread shallow water carbonate deposition with some terrigenous input. Also, a large volume of regional Jurassic magmatism that we used in our hypothesis when we wrote these proposals as seals. And our first project was focused here on the South Georgia Rift Basin onshore, and then we moved with this project I'm going to show today offshore in the Atlantic. Some of the major sedimentary deposits here from north to south include the Carolina Trough, the Southeast Georgia Embayment, and the Blake Plateau, which sometimes they range in sediment column thickness from 10,000 to 23,000 feet. Geophysical and stratigraphic studies suggest that the Jurassic section is at least 4.6 miles thick in the basin and thickens seaward. And the Cretaceous section is characterized by more clastic sedimentation in the north and more carbonate deposition in the south, forming a large carbonate platform over the Blake Plateau and the offshore Florida. So these were some of our project objectives and hypotheses that the Mid-South Atlantic margin would store about 780 gigatons of CO2 in the Mesozoic formations. And here are the requirements from the Department of Energy in terms of depth and in terms of volumetric capacity. And actually, if we look here, these are all point sources of CO2 in the Southeast, and it's about 40% of the nation's CO2 from point sources is actually emitted from the southeastern United States. The geophysical data set used for this analysis includes 2D multi-channel seismic reflection data collected by the U.S. Bureau of Ocean Energy Management in the late 1970s. So we are talking here about legacy data, legacy 2D seismic data. We also used 3 wells, 3 of the 7 wells that have digital logs necessary to implement acoustic impedance inversion and conduct integration with seismic data. The other 4 wells have some reports, however, only the 3 of them that you are gonna hear me talking about, and they are all here in the Southeast Georgia Embayment. They are COS G1, Exxon 564, 1, and Transco 1005-1 wells. So, here is the area that I will focus on, and it is because this was the denser information that we had. So there is no 3D seismic in the south, in the Atlantic, and it's still under a moratorium. We can talk more about that in the Q&A, what the situation with that is. However, this is all vintage data that we had to work with, and that's why we use this model-based inversion that actually is pretty good, or at least it gives pretty good results, even when limited well control and poor quality seismic is all you have. So acoustic impedance, the product of rock density and velocity, can be used as an indicator of lithology and porosity, which are both important for CO2 storage assessment. Acoustic impedance provides a more detailed subsurface geologic image than the conventional seismic section, because the reflectivity coefficient on the conventional seismic section captures the layer interfaces, while the acoustic inversion is a layer-based property and focuses on the layers themselves, which is basically what we are looking at. However, extracting acoustic impedance properties from seismic data requires seismic inversion, which implies converting seismic reflection amplitudes into impedance profiles. And shown here is a workflow that was created by my student, Khaled Al-Mutairi, and we were able to replicate that, as I'm hoping to show today, in the Anadarko Basin. The first step was to extract a statistical wavelet from a nearby seismic line to be composed with a reflectivity series from the sonic and density logs. And that was in order to generate a synthetic seismic trace from the well logs. So this synthetic seismic trace was subsequently correlated with the actual seismic trace. And therefore, seismic well time analysis has been conducted in this case to compare the well logs that were measured in depth units with seismic data measured in time by creating the time-depth relationship using the sonic log and the check shot. So here on the left, I show seismic to well correlation achieved by matching events on the synthetic traces with the same events on the seismic trace at the Transco 10051 well. And the figure here on the right displays the initial model for the acoustic impedance and the post-tax seismic inversion analysis results at the different well cost G1. And this is the only well where we actually did have some poor results as well. So here, this figure B shows a reasonable match between the inverted acoustic impedance shown in red and the computed impedance from the well shown in blue. And here are the synthetic traces and the traces extracted from the seismic shown side by side in red and black. So in order to constrain the results, Khaled used all of these different types of algorithms for his model-based inversion. And the color-coded bars here represent acoustic impedance values, and from low here to the bottom to high at the top. And I'll only show results from the upper Cretaceous and only speak briefly toward the end about the lower Cretaceous capacities. Trying to Can you still see my pen?
Okay. Your pointer, no.
Okay.
Yes, it's back.
It's back. Okay. Sorry, I lost it. Okay, so going through the workflow, furthermore, the porosity was calculated at the wells, extrapolated with QC to the available core data that we had from the CAS G1 well. And here on the left, we show calculated porosity logs from the CAS G1, Exxon, and Transco. So all three wells that we had for the study, and the extrapolated porosity from inversion at the CAS G1 well only here on the right. So using density and neutron logs, total porosities were calculated at all these three wells in two steps. The first one, we used the density porosity relationship shown here by Serra, 1984. Here formation bulk density is a function of matrix density, porosity, and formation fluid density. And step two involved using neutron density, that is a function of matrix density, porosity, So here in the neutron density logs was used through this relationship by Gaymard and Upon 1968. And this was another way to estimate porosity distribution as a derivative from simultaneous inversion. So here in this process, we use the CGG Hamsel-Russell software package in order to provide the porosity model shown here on the right side by involving the porosity log, the top and the base of the horizon as they were picked on the seismic, and the acoustic impedance, all of them as a guide model for the geometry of the interfaces. The gamma ray log shown in here that measures the natural radioactivity in the rocks, overlays the porosity section in this figure on the right, and that's the thick line, in order to determine the shale strata intervals that we use as seals. And as seen, the porosity measured from the core at the G1 well, we believe it matches well the inverted to the porosity section, which we thought it was good or important for quality control. The acoustic impedance plot shown in this figure indicates that the upper Cretaceous strata of the South Georgia embayment have two prospective intervals at the Transco 1005 well. The first one represents an impermeable sill, which is the layer between the top of the upper Cretaceous and the Turonian surface. That shows high impedance that is interpreted as low porosity. They are inverse proportional. And the second layer represents the interval between the Turonian and the base of the upper Cretaceous that may prove to be a significant reservoir for CO2 storage. And that's what I will focus on. So the previous results are similar to the impedance inversion values at cost G1 well now, which show two strata intervals within the potential interval. And here, it's a zoom in of this acoustic impedance to this plot. So the lowest impedance values are located where the highest porosity is and vice versa. And furthermore, is correlated with poor porosity where available. We don't have too much of that. But therefore, we believe that with a proper workflow and analysis, the acoustic impedance inversion could be a successful tool to discriminate lithology and estimate porosity, especially where well data are sparse, like in our case. So we do this furthermore, and we use cross-plotting to link the acoustic impedance with porosities that were either calculated from the density and neutron logs, as I showed before, or measured from pores. And these figures show P-wave acoustic impedance on the x-axis, all of them, and the percent porosity on the y-axis. The dots here are color-coded by depth, and the figures show a linear regression between the acoustic impedance and porosity at the cost G1 well here at the top, and Transco 1005 well at different levels or different intervals here at the bottom. And we use this correlation, this was 0.75 further to derive permeabilities from porosities. So using the porosity and acoustic impedance relationship from the previous slide, the porosity distribution is extracted using the linear regression with the best correlation coefficient, that is the one I said, 0.75 at the cost G1 well. And that was here on the left, and we also did that for the Transco 1005 well at different depth intervals here on the right. So this slide shows a report from 1978, and basically that's the only one that has information about pore porosities and permeabilities, and that's from conventional and sidewall pores at the cost G1 well. The lower part of the upper Cretaceous interval at 5,500 feet has porosities of about 20 to 35% and permeabilities of 450 millidarcy. And, relatively speaking, this was the largest that we had. And we believe that that makes this a candidate rock for reservoir. Here in B, we show the porosity and permeability relationship as a function of depth from the pore data. That is shown here in A, and this relationship supports the previous study that was conducted by Al-Mutairi et al. That was his first paper, 2017, which proposed that the upper Cretaceous strata have two significant potential storage reservoirs for CO2 separated by a seal. Here in C, we show the permeability distribution estimated using a regression relationship between the core porosity and permeability. A least square exponential fit was used here to predict the permeability distribution as a function of porosity that was extracted previously from the acoustic impedance. And then we, basically extrapolated that throughout our volume. And volume, again, this was 2D data, but Khaled was able to bin the data and create a pseudo 3D volume out of the denser 2D seismic lines. Here, a 3D velocity model, because we had to convert the volume from time to depth, and another of my master students, he was able to use vintage refraction and reflection data, basically looking at scans at the stacking velocities at the top of of the seismic sections, that are all scanned, and basically put those in a database and create a 3D velocity model for our study area. So we were able to use that to convert the time to depth. And this is just a 2D velocity cross-section, but he created a 3D model. So some of the structural maps that were generated from that, some of the significant markers in the Upper Cretaceous, Lower Cretaceous, and Jurassic, and those were all prospective, but we had basically 3 students working on all of these, depth intervals. Khaled only, focused on the Upper Cretaceous, and that's showing, his workflow here. But since this geologic province has conformable deposition, lateral facies changes, we think may be of greater interest in the study area than in other basins along the Atlantic offshore margin. And, here showing the prospective, the thickness maps of the prospective seals and the reservoir. All right, so the main potential reservoirs in the Upper Cretaceous strata identified in this study are within limestone deposits with significant interbed sandstones, shales, and dolomites. Reservoir A in this depth interval that is sealed by about 725 feet thick shale. That's Reservoir A, and Reservoir B that is deeper, sealed by 160 foot thick shale. It basically separates the 2 interpreted reservoirs. So we believe that we found significant markers in the Upper Cretaceous and the Lower Cretaceous sections. Here I'm showing both of them, even though I mostly focused on this. Here for prediction of CO2 storage capacity, we used the 2008 DOE equation used to estimate the same reservoir storage capacity, and that's the equation we used. Based on the porosities, reservoir thickness, and we do the density of supercritical CO2, from the literature, and here the CO2 storage efficiency factor is usually the wild card, unless you really have core data to do the analysis on. You kind of have to take that, from the literature based on the types of rocks you have, and it varies from, this P10 to P90. So basically, the CO2 storage efficiency factor reflects a fraction of the total pore volume that is filled with CO2, basically we came up with these estimates for CO2 storage capacity, depending on how you vary the efficiency factor from anywhere between 9 gigatons, these are all in gigatons, to about 96 gigatons. Let's say in average would be about 32 gigatons CO2 storage capacity, much larger in the lower Cretaceous, but again, I didn't show that. This is the other student who is still working on the Lower Cretaceous and the Upper Jurassic. One of our other students took this model created by Khaled with, again, lower and upper reservoirs in the Upper Cretaceous and the 2 seals. Took this and did a 3D injection simulation, he investigated the porosity and permeability variations within the 2 identified reservoirs, as well as the proposed seals due to either tensile failure and potential CO2 plume linkage. So basically, the highlight here was that the effects of mineralization and tensile failure due to increased induced hydraulic pressure that were both investigated show that basically without mineralization, the tensile failure is great, and the seal would perhaps collapse. However, with mineralization, the model showed that while initially the dissolution of CO2 plume during the injection period enhanced the porosity, reducing the seal stability, after the 50-year shutdown, according to the DOE standards, the dissolution slowed down, approaching equilibrium, and then caused precipitation to become the dominant process. So the mineralization, that was, I'm realizing that I am now at 6:41. So maybe I will spend the next 5 minutes. If I had to, let me do that. To just give some highlights about the Anadarko Basin. And actually my student Payden through it. She's keeping a poster at the APG Mid-Continent in Tulsa, if you go there. But basically, she implemented the same workflow, but here we had a denser seismic coverage. We had two 3D seismic surveys from EOG, and then we had 17 wells, although not all of them, had quality data. But the main objectives for this study were to evaluate the potential for carbon utilization in the Cleveland formation, and carbon storage in the Skinner Formation, this is the stratigraphic column. I'm not going to go, so Mari Turco is going to give a talk next month, I understand, on the Anadarko Basin. But, basically this is our location area. I'm not going to go to the geology of the Anadarko Basin. I'm actually new to the Anadarko Basin. This was my first exposure to working in the Anadarko Basin. And we are very excited that this project sounds promising. These are some type logs and isopath maps of the Cleveland with high stand sands, incised valley fill, and capping transgressive shallow marine deposits. The Cleveland is a little Pennsylvanian interval sourced from the west, east, and south. The westerly source Cleveland thickens from the northwest to southeast. Interfingering with carbonate beds along the northern shelf and grading into the granitic wash along the southern Amarillo and Wichita uplift boundary. And lithologically, it consists of silty shale, interbedded siltstone and sandstone, and interbedded carbonate and sandstone. Skinner, here, showing the paleogeography of the mid-continent during Skinner deposition and local depositional environment southeast of our study area. But the Skinner is one of the Desmoinesian sequences composing the Cherokee group. It is dominantly sandstone and shale, representing high stand progradational fluvial deltaic complexes that were incised by low stand valleys, subsequently filling and forming the reservoir trends. Anyway, moving here, showing the Cleveland carbon storage potential, the reservoir and the seal. And here on the left, that's the spatial, okay, so the Cleveland shows intervals of high porosity overlaid by low porosity. So basically, Payden did the same workflow, did the same exact analysis, and these are just the resulting thickness maps for the reservoir and the seals for now Cleveland, and I will show Skinner next. So the main producing reservoirs for the Cleveland Formation were the incised valley fill and high stand deltaic sandstones that the valley system incised. And we find here thin, transgressive, shallow marine deposits that cover basically areas over our surveys. And this and thick overlying mudstones could serve as a seal for the main reservoir sands of the Cleveland. The Skinner is tight, is a tight, thick formation with intervals of relatively higher porosities overlain by the Flu Formation that is a potential seal and is absent of sandstone in the study area, and it is predominantly shale. And within this Flu Formation is regionally extensive over at least our study area. And here are some of the volumetrics calculated for Cleveland and Skinner. We only did Skinner for the southern survey. These are north and southern surveys for the Cleveland. With an efficiency factor, again, we didn't have the numbers. We took numbers based on lithology, based on this paper by Goodman et al., 2011. So these are some volumetrics, and these are in megatons. So now taking the efficiency factor, from P10 to P90, these are potential volumetrics for our study area. And I am going to conclude here for our SOSRA project. We believe we have a good workflow for model-based inversion to discriminate lithology and predict porosity in the absence of having good quality data. Those were some estimates for storage capacities in gigatons. And, we believe that we do have potential reservoirs and seals that meet the DOE criteria. And for the Anadarko Basin, we were happy we could replicate the workflow for model-based inversion. I didn't say we got this data in the depth domain. We didn't have to convert it from time to depth. It was all depth migrated. And these are some of the estimates, megatons, not gigatons in this case. But again, we are looking at tighter rock formations, just in general. I'll leave it here, and it is 6:47. I'm sorry, Patty.
Well done. Well done. So Camila, we do, first of all, thank you so much for presenting this to the Houston Geological Society. And one of the things I find interesting when we talk a lot about CCUS and other aspects besides petroleum geoscience, it's interesting to always see that the workflows, the understanding of the subsurface, there's a lot of similarity in what those of us that have done careers in the petroleum industry, that skill set is the same skill set that's required to work out some of these problems of how we're going to tackle this issue. So thank you for going through that.
Absolutely.
Yep, go ahead.
Well, it really is important. It's the same skill set because we are training students. And we are impressing on them, that they need to learn the fundamentals, that the fundamentals are exactly the same. Yes, and then, you may want to, become a little more interdisciplinary or, take some engineering courses, maybe some data analytics now, but the skill set really is, the same unless, things change, dramatically with, innovative technologies in the future.
Right. So we do have a few questions. The first one is from Lawrence Walker. Would the models predict a 4D response in the injected reservoirs? And if so, would it be dominantly related to a pressure increase or CO2 displacement of brine?
Well, that's definitely a great question, Lawrence. And that's what projects that inject CO2, either at the pilot scale or at the commercial scale, need to do. They need to do the 4D, the time-lapse monitoring of the plume. What we did only characterization. So we did that injection simulation in the absence of having any injection. It was basically only based on the model. And, so we used the layering and then we used, some faults with different permeabilities, but we really didn't have the data. Again, we didn't have any injection, in any of these projects. And, you kind of have to do that and in order to monitor it. And then, see where the issues is, I'm not answering really your question, but we just don't have that kind of data for for the work we've done. I wish I was involved with one of those carbon safe projects, like Kemper. Actually, so Jack Bash, is involved with that. He started on that when he was at Alabama, but they are injecting. They've been doing pilot injection, and now they are taking it, to the commercial deployment, and doing all of the monitoring, including microseismic, injection simulation and all of them.
That'd be good. Maybe I can follow up with Jack and see if we can get him to come do a lunchtime talk on that topic. So we have another question. This is from Jim DeCinia. I hope I'm pronouncing that right. While your workflow for the seismic is standard practice, it has uncertainties even with well control. Do you capture and carry ranges of inferred lithology, porosity, permeability, thickness, and lithology uncertainty? Do you see these uncertainties influencing rating and contrasting of potential storage reservoirs? So how does the uncertainty tie into how you would classify a good potential reservoir versus a marginal potential reservoir?
Yeah, that definitely is a great question. We haven't done that because, this that we looked at, they are not yet considered to be prospective for CO2 injection. We wish they were, and DOE may decide to go offshore to start doing some of those carbon safe projects and perhaps take it to that level. We definitely, there are many uncertainties. There are uncertainties basically, from the acoustic inversion, model. We did not have, okay, so for the Upper Cretaceous part of the workflow that I showed, we didn't even have any core data. That is critical, of doing this analysis. We did have core data for the Lower Cretaceous and the Upper Jurassic that I'm actually not showing in here, because it's still work in progress. And one of my master students took that core data from the Delaware Geological Survey, that's where still is in the repository to the DOE NETL lab. And that's when, he was able to do more detailed analysis and even coming up with this, more robust storage capacity factors, because that's a big unknown. Even if you, really, know your lithology, your anything, but that's all we had. Basically, what I showed you, it's all legacy 2D seismic data and legacy papers, so we used core data to create that regression curve between porosity and permeability from a paper, because all of the core has been destroyed, all of the core that was, that still existed, the Delaware Geological Survey, those were wells from the 80s. So
yes, Janet Combs had made a comment. It wasn't really a question that she'd work exploration in the Southeast Georgia embayment, the Blake Plateau, the Carolina Trough in the late 70s. And a lot of those projects did close down really quickly. And it's a shame that a lot of the core data doesn't exist anymore, because that would be critical data. And then,
only one well still had core, and that core was only from Lower Cretaceous and Upper Jurassic as far as our interest was.
So we have one last question from an anonymous attendee. Could we use a depleted mature field potentially as a deposit reservoir, as a reservoir to inject into?
Oh, absolutely. And that's basically what CO2 injection has been used for, right? It's EOR and EGR, so enhanced oil and enhanced gas recovery. And even this, you may have heard about the incentives that one of them is 45Q, that I think was, it became live in 2018. So basically, that gives a tax break both for saline aquifer injection and EOR, but it's like $50 for saline aquifers and $35 for EOR. But like here in Oklahoma, what I hear is that operators, have been using CO2 instead of water since the 70s.
Yeah.
For EOR and EGR. The problem is that, about 50% of that comes back. It really isn't, it's not as reliable, I would say, as a good saline aquifer with, good properties, including CO.
So one more question. in fact, I had this too. So yay, Kathleen. Says, apologies if I missed it, but can you comment more on your E variable, CO2 storage efficiency factor?
Yes, so we took those from the literature. We did not have core to actually go and obtain enough data to come up with better CO2 storage efficiency factors. So we basically used that paper, Goodman et al., that I showed based on various lithologies. It gives various efficiency factors, and that's why when we report to DOE, we show the whole range from P10 to P90 because we just don't have the data to show what it is, and we kind of average it as P50, say 50% of the pore space would be occupied with CO2. But that is a big uncertainty, and unless you have the core to do more detailed analysis, you just get a range.
Yeah, so in a roundabout way, that's coming back a little bit to Jim's question about how do you deal with the uncertainty and without the rock data. So we have one more question. I'm going to throw this in real quick. Have you done hydrocarbon content analysis on the core that you do have?
No, we have not. We have not. It was not part of the project, so it was basically, geophysical, analysis. And as I said, I have a student who took the core to Nettle and did some scanning on the core to come up with better efficiency factors for the lower Cretaceous and the upper Jurassic. He graduated, but it was mostly to constrain better those volumetrics. We haven't done anything else with that core.
Okay, I think that has answered all of the questions. Camila, if you can stop sharing your screen for a moment. There we go. And I think then it's back to you and I. Thank you so much for doing this presentation for us. I think what we're all seeing is that there's a lot of work to be done, both in private industry and in the academic world, to be able to look at these potential target reservoirs and look at where we can have these robust injection projects. It's also speaking to the fact that sharing of data, we have a lot of core in these core facilities that different industries and universities have, and a lot of that core is aging core. And to get access to rock data, I think is critical. OSU actually does have a core facility to be able to go in and maybe take some of these cores that people might know about that would be good target reservoirs to then let these students utilize to do this research on. So with that, sorry, Camila, did you want to say something?
Yeah, we have several students who do work here. I mean, I do geophysics, but, Jim Packett, his students do core analysis, more for unconventionals, not necessarily for CO2. I mean, you still need to have projects funded, for CO2. And so those projects, we have one right now ongoing to look at storage capacity in Oklahoma. And yes, I mean, those are things that are part of this ongoing, these are all ongoing studies. I would say it's a lot to do because sale informations is still in the infancy right now. And, these are all, emerging, I would say, in various shapes and forms.
Well, so on behalf of the Houston Geological Society, Dr. Knapp, thank you so much for giving this presentation for our community. I would encourage everyone to go to the Houston Geological Society website, look at our upcoming events. Our next general dinner technical talk will be on October the 11th.